Okay, so when they want you to do things like that, John, the directions are going to say compare. So if they want you to find the greater number, it's going to say compare the two integers, circle the greater number. But that's not what these directions say. They say to identify something called the greatest common factor. Greatest common factor is just the biggest number that goes into both things. So for instance, 6 and 15, what's the biggest number that goes into both of those, John? It is 3. That is the correct answer for number 1A. Does anybody have any luck with 1B? Notice there's only an X in one of them. What do you think, Nikki? It is just 3 again. Why not an X, Nikki? Yeah, you're right about that. What about part C? What's that? It is just X. Why not X squared? Yeah, they don't have 2 X's in common. It has to be a common factor. Bless you, Nicolette. It's just 1 X, you know. Did anybody have any luck with H? That was our, it's supposed to be D there, by the way, but it's an H for fun, I guess. Nikki. Yeah, very good. Questions about that? Sounds like you guys had a pretty good job, or did a pretty good job with the warm-up. I'm going to go ahead and show you your answers here. So all in all, the answers to your warm-up, that is what they should look like there. So yeah, you did say 1A was 3, 1B was 3, 1C was X, and then 1D there is 3M squared. Number 2, distributive property, 3x squared plus 6x. Part B is x squared minus 4. Part C, check it carefully. Remember, this isn't time for you to sit back and take a vacation. You're checking your work. Bless you. For part C, essentially what you had to do to get that answer, you had to FOIL, right? 3x plus 2 times 3x plus 2. Keep in mind that produces an OI term, a middle term there of 12x. And then part D, you have 6x squared plus 7x minus 3. Did anybody have trouble with their FOIL or distributive property? Because if you can't FOIL, you cannot factor. It's kind of impossible to do. In my experience so far, in your pre-test, you guys could FOIL. You did a nice job, so I'm pretty confident moving forward. Number 3, perfect squares. You had to list the first 15. They start with 1, stop at 225. Questions there? Okay, so I didn't do what I like to start off with on Mondays. You know what I like to do on Monday? I like to read through the agenda with you so you have an idea of what's coming at you this week. What you're going to see is you look at that agenda that you grabbed when you walked in. You'll see that Monday, Tuesday, Wednesday this week, I just show you the different methods for factoring. So today we're going to focus on specifically the GCF method and then a method called special cases. So that's that. And then tomorrow we start factoring trinomials. We factor trinomials when A equals 1, and on Wednesday we factor trinomials when A does not equal 1. Thursday we bring all the methods together, we do a big review day. Friday is a quiz. Did you see that? 25 questions. And I'll also field questions from your review before you take that quiz from me on Friday. 25 questions, 25 points. It's either right or wrong. Okay. Questions about what's going on this week? Any field trips or anything I need to know about? We're all good? Sweet. Okay. So our methods for today. The GCF method, and they're called special cases. When I teach special cases, I actually have a different way of doing it. The methods we're going to talk about today, the GCF method, of course, and then I don't call special cases like your book does. I actually say we're going to use the square root method. So 2 methods are coming at you today, the GCF method and the square root method. Now, I've been teaching factoring for a long time now, and let me just talk to you a little bit about what it's like to teach students factoring. Okay, here's like inside, behind the scenes view from what I see. Students, when I teach them a method, I feel like a wizard. I'm like, I am good at this teaching thing. Like, I can teach a method like up there with the best of them, I'd say. So in an isolated little bubble, these methods are very doable in my experience. Like, I present it, students can do the method, I walk around, I see it, everybody's getting the right answer. I'm like, this is the best day ever. But then, in some years when I've taught factoring, I go to give a quiz, and I'm like, holy cow, what happened? So over the years, what I've come to understand is that when they're in a little bubble, my students are very good at it. You know, what I mean by in a little bubble is like, oh, if I say use the GCF method, you can use the GCF method. Or if I say, hey, factor using the square root method, you can do the square root method. But when I mix them all up, you're like, oh, what do I even do? So as I go through and teach the methods to you and what we're going to practice doing, we're not just going to do the problem, but I'm going to say why I'm doing the method. What I need you to think about as we're doing each problem is why is she using this method? So you're not only just doing the problems, you're understanding why we're doing what we're doing. That way, when you see them all scrambled up, you recognize that a certain type of problem gets done in a certain type of way. So that's what I kind of want you to think about as we move through today's lesson. All right, with that, the first method is called the GCF method. It gets its name from the very first step. The very first step in the GCF method is to identify the GCF, or the greatest common factor. And like I said, you should be asking yourself, Mrs. Lucas, when do I use this method? Like, what types of problems do I use this method on? Honestly, you use this method every time you factor, every single time. Step one in every single factoring problem that we do together as a class, step one in every single problem is to always try this method first. You always have to try to take out a greatest common factor, because if it's in there and you try any other method that I teach you, it will mess up your day. So please make sure that you always try the greatest common factor method first. So as I said, step one is to identify what that common factor is, greatest common factor no less. Identify what that greatest common factor is between your terms. Step two is to perform sort of the reverse of the distributive property. And then the third step is to check. So giddy up, let's do it. If you take a look at part A, we have 6x to the third minus 4x. So the first thing I have to do is identify what these two terms have in common. So I look at 6x to the third and 4x. And I'm like, oh, 6 and 4. Those are both even. So they have 2 in common. And I think Tessa was saying this earlier. You know, if you want to identify the letter that you should pull out of the problem, it's going to be the letter that has the smallest exponent, because that's going to be how many x's they actually have in common. So if I'm comparing x to the third and x to the first, x to the first is what they have in common. So that's me finishing step one. The GCF between these two terms in yellow is 2x. Remember, you don't write it down if you don't understand it. So if there's a 2x on your paper right now, you understand why it's there, right? Okay. All right. Now I'm going to open up a set of parentheses. This set of parentheses mimics the original size of the problem. So this set of parentheses is going to hold a binomial, something with 2 terms in it. And then I kind of do the distributive property with a fill in the blank. So I ask myself, more or less, 2x times what gets me 6x to the third? Do you know, John? Okay, so 2x times what gets you just 6x to the third? That's good. So 3x squared answers the question, yeah. Because 2 times 3 is 6. X times x squared is x to the third. Then we bring down our minus sign. And John, I think you also wanted to contribute to this last part, right? Yeah. 2x times 2 gets you 4x. You check it with the distributive property. So we ask ourselves, 2x times 3x squared, that is indeed 6x cubed. And 2x times negative 2 is, ooh, sorry. So we had 6x cubed minus 4x. So I did my distributive property, and look, I got the original problem back out. If you don't get the original problem back out, you messed up. Try again. Part B, I put this in here because it comes up a lot. Do you see how the A value is negative? And what I mean by the A value is that these coefficients go in alphabetical order. We usually call this guy A, this guy B, this guy C, right? What I want you to draw your attention to right now is the fact that there's a negative 4 in front of the x squared. Literally, when this A value is negative and you don't factor a negative out of the problem, all of the other methods that we try get all messed up. If you tried AC grouping, if you tried completing the square, if you tried the quadratic formula, I see lots and lots of mistakes when people leave this A value negative. So as I look at the rest of the problem, it says negative 4x squared plus 12x minus 16. As I read that problem, I notice that 4, 12, and 16 are what we call multiples of 4. In other words, they're all divisible by 4. Furthermore, because this 4 out in front is negative, I want to get rid of the negative. So instead of taking out a positive 4, I'm going to go ahead and take out a negative 4. Notice I didn't pull out any x's with this negative 4. Can anybody comment about that? Why didn't I factor out any x's? What, John? Very good. The negative 16 doesn't have an x, so it's not in common. Now I basically do that distributive property thing in reverse. So I have to ask myself, negative 4 times what gets me negative 4x squared? Answer there, x squared. And then I got to ask myself, negative 4 times what gets me back to positive 12x? It's going to be negative 3x. And then negative 4 times what gets me back to negative 16? That has to be a positive 4. So make sure you watch your signs when you do this. If we check with the distributive property, I'm hoping I get my original problem back out. Negative 4 times x squared is negative 4x squared. Negative 4 times negative 3x is indeed positive 12x. And negative 4 times positive 4 is negative 16. So that totally checked out. Both of those answers in red matched my original problem, so I know I did the GCF method correctly. Okay, are there questions about that method? Because I have one method left, and then you get to practice. Alrighty. The last method that I'm going to teach you today takes care of two types of problems. It's called the square root method. And notice the title that it's accompanied, or that it accompanies, bless you. Do you see those things I just highlighted in yellow there? Notice I'm going to use the square root method on both of those types of problems. What do those types of problems have in common? Those phrases I highlighted in yellow, what do they have in common? John? Yeah, perfect squares. Very good. You can't do the square root method unless you have perfect squares hanging out in your problem. And if you forgot what perfect squares are, well, you already listed out 15 of them in your warm-up today. So your eyeballs, how do you know? Remember I said that's our big idea, not just the method, but how do you know when to use the method? Method 1 today, the GCF method, we use it every time we factor. You have to try to do that method first. Method number 2, how do you know you're going to use this method? Any one of those 15 numbers will be hanging out in your problem. You would try to use this method. Doesn't always work out. If you foil it at the very end and you don't get the original problem back out, well, then this wasn't your method. So if you see any of these 15 numbers in the problem, you would try this method. So let's get started. Oops. Oh, sorry, I forgot that was my completed slideshow there. Okay, so if you take a look at this middle row of our chart here, the first type of problem that we can use the square root method on is what we refer to as a difference of two perfect squares. The form it comes in is this. A difference of two perfect squares has something squared minus something else squared. That's the form that it comes in. To populate the parentheses that we would FOIL to check, you take the square root of the first part and the square root of the last part. If you take the square root of the first part, you get your firsts in FOIL. And if you take the square root of the last part, you get the lasts in your FOIL. Notice what signs always go in between. This is the case where we need our outers and inners to go away to get those two terms. So do you see how there's always going to be a plus and a minus in your parentheses? So for instance, part A, x squared minus 4. You've already seen that problem today. Oh, where'd you see it? X squared minus 4. You handled that already today. Where'd you see it? I like how some of you are flipping back, looking around a little bit. Where'd you see it? X squared minus 4. Look at your paper. It is on there. When you see x squared minus 4 on your paper, put your finger on it. You see it? Ooh, it's in the warm-up. Eddie, are you okay? Yeah? Do you need to go to the nurse? Okay. You have your notes? Where are your notes? Oh, just on your lap there. Okay. Oh, you're still on the right page. Everybody see it? Yeah. All right, so just to go back, x squared minus 4 came out of U, foiling part B in number 2. Notice what happened. Your outers and inners canceled. They went away because you had opposite signs in your parentheses. So these two things are sort of opposites of each other. Wow. They're actually equivalent to each other. Who am I kidding? This equals this. But it's like one is a different form of the other. One is the factored version. The other is what we call an expanded form. So with that, you already know the answer to part A. This guy factors to be x plus 2, x minus 2, but let me show you the method, okay? So I'm going to go ahead and take the square root of the first part, square root of the last part. The square root of x squared, square root of x squared, that's just x. Square root of 4, that's just 2. If we keep in mind that we're supposed to be able to use the distributive property, which is FOIL, in order to get the original problem back out, I need this first sign to be a plus and this second sign to be a minus. Now if I FOIL that, x times x gives me x squared, negative 2x and positive 2x is 0, and then positive 2 times negative 2 gets me the negative 4 at the very end. It'll work for part B as well. Take the square root of the first part, you have 16x to the 4th. Square root of that is 4x squared. Square root of 81, that's 9. Put a plus and a minus. I am not done with that problem. I can factor it again. Does anybody see what factors again in that problem? See it? Nikki. Yeah, you have to square root which one again, because only one of them is going to do it. Both of them? Just the one. Yeah, very good. Remember, it's called a difference of two squares. So this guy here factors again. You'll see on my sideboard right there, I showed my students 4x squared plus 9. All the reasons why that doesn't factor. 4x squared plus 9 does not factor. Let me show you how 4x squared minus 9 does factor, and then I'll talk more about that in a second. So 4x squared minus 9, I could square root method that again because it's a difference of two perfect squares. So what I'm saying is 4x squared plus 9 doesn't factor. That's going to come along for the ride. And then I could square root method the difference of two perfect squares. So the square root of 4x squared is 2x. The square root of 9 is 3. And then I have to put a plus and a minus in my parentheses there. So now that is completely factored. Let's talk about why 4x squared plus 9 doesn't factor. You don't need to write this part down. I know, you're getting a break. What's going on the smartboard does not need to go in your notes. This is like purely for your visual entertainment. I always forget that one doesn't work. And we're talking about 4x squared plus 9 right now. It is not a difference of two squares. difference in math class means to subtract. This is what we call a sum of two perfect squares, and it doesn't factor. If you tried to use the square root method on this, humor me for a second. Together, let's just try to square root method this and see if we can get anything that foils to give me 4x squared plus 9 back out. If I tried to square root method this, I'd have 2x and 3, 2x and 3. Then you have to figure out what signs you have to put in there. So it said plus, let's try pluses. Well, if you FOIL this, you get 4x squared plus 12x plus 9. Oh, it's not the same as the original problem because there's no 12x in the original. So this isn't right. We could try to square root method it again and put minus signs in there. But if we FOIL that, what you end up getting is 4x squared for your firsts, minus 12x when you put together your outers and your inners, and then plus 9 at the very end. Again, we get this vexing bx term in the middle. So this doesn't work. You could once again try 2x plus 3, 2x minus 3, but you guys know what that yields. Oops. That's going to yield 4x squared minus 9, which is not 4x squared plus 9, not the same thing. Now, if this argument here isn't convincing enough as to why a sum of two perfect squares doesn't factor, I ask you to consider this. All of these x squared things are what we call parabolas when you graph them. This particular parabola has been moved up 9 spaces, and it's super skinny. When we go ahead and factor, the big idea is to be able to find the places. Listen carefully. You ready? Because you're going to have to look at that picture. When we factor, the big idea is to be able to find places where the graph crosses the x-axis. So Darius, please tell me how many places that parabola I just drew, how many times that parabola crosses the x-axis? Yeah, none. Not a 1. In other words, there are no possible solutions, real solutions, for x, making it not factorable. Because when we factor, you get real number answers. So because this thing does not cross the x-axis, it can't have real number values associated with x, and therefore it isn't factorable. So that's another reason why we can't factor a sum of two perfect squares. You can only factor a difference of two perfect squares. Okay, part C. We have 12x squared minus 3. 12x squared minus 3. I'm like, oh my gosh, Mrs. Lucas, you just told us to look for 15 different numbers. And I don't see any of those in this problem. So why on earth is it lumped into a difference of two squares? Go ahead, John. You always have to try that method first. You always have to try the GCF method first, even in these early examples. You're absolutely right, Jonathan. Nice job. You could take out a greatest common factor. The greatest common factor is going to be 3. And then what's left over is 4x squared and a minus 1. Now that is a difference of two perfect squares. So I'm going to square root method this guy. Don't forget to bring your GCF along for the ride. This is going to factor to be 2x plus 1. And then 2x minus 1 when you use your square root method. Last type is the perfect square trinomial. So again, what I'm going to see are your first and last terms. Those are going to be perfect squares. That's the forms that it comes in. Furthermore, your last symbol in the problem is always a plus. Ultimately, your test is going to be to FOIL these to make sure that you get the original problem back out. So sometimes it'll be set up so that that middle term isn't 2 times u times v. You have to check these with FOIL because sometimes it'll be set up so that when it FOILs, it actually doesn't give you the original answer back, or the original problem rather back out. I'll show you what I mean by that. I am going to use the square root method to help me just initially populate my parentheses. Square root of 16x squared is 4x. Square root of 9 That's 3. Now I need to figure out what symbol goes in between. My outers and inners right now, bless you by the way, make 12x and 12x. How could I put those together to make 24x? What kind of symbols? What do you think, Andy? 12x and 12x need to come together to make 24x. What symbols are you going to use? And that would make 0x. If I had positive 12x and negative 12x, that makes no x's. 2 positives, very good. That was supposed to be a plus sign. So yeah, we have 4x plus 3, 4x plus 3. That would FOIL to give you 16x squared plus 24x plus 9. Square root method on the last one. Watch out, because this time around I think they switched the signs on you, right? We have to make a negative 10x in between. So I'll populate my parentheses. The square root of x squared is x and x. The square root of 25 is 5 and 5. Now I'm going to check my outers and my inners. They need to come together to make negative 10x. You guessed it. You have to have a minus sign in both of those to make negative 10x. One last thing before I cut you loose on some closing examples. 4x plus 3 times 4x plus 3. We never really write it like that because we're big kids and we know better. 4x plus 3 times 4x plus 3. Anybody know a nicer way to say that? Nikki. We say 4x plus 3 quantity squared. Real close. If you just say 4x plus 3 squared, that sounds like 4x plus 9. So you gotta have to throw the quantity in there. It's the quantity of 4x plus 3 squared. Thank you, Nikki. You're pretty much right, though. I understood what you were saying. X minus 5 times x minus 5. We actually write that as x minus 5 quantity squared. Alrighty there, kiddos. Let's see what you learned today. You're going to try these for me before you leave. Please notice that I think there's a typo in your note packet. It's on part B. I fixed it here, but I don't know if I fixed it before I sent your electronic copy. This should be in part B, negative 12x squared. I think yours says cubed. If it's cubed, that thing's not really factorable. So you please adjust that for me. So you have those 9 problems to try real quick before you leave. And then the additional questions at the bottom, you should also try those. Make sure they're done definitely for tomorrow if you don't finish them in class today. I'm going to show you the answers to these in just a minute. People at home would need to see these, huh? So we'll talk more about this tomorrow in your conclusion. That'll be it.